Okay, there's this problem up here you can get started with. So write that vector as a linear combination of those other vectors if it's possible. How's everyone doing? Anyone had their first midterm yet? We like to do the same. Since all the professors like to either have 2 or 3 midterms, they all start lining up in the same week. I had one student, the week of I was teaching calculus, she said, I have 5 midterms this week. And I called my mom to complain, and she just said, welcome to college. So, yeah. But yeah, they all line up, then you get past them, and then you get a few weeks off. So, who'd like to offer a prayer for us? Anyone? Anyone? Who'd like to offer a prayer for us? Gosh, that's a way to quiet the crowd. Go ahead.
That we'll comprehend these concepts and that we'll be able to apply them and working for a professor and I guess it'll be a lesson as well. So it's great.
Amen. Thank you. So the ideas of span and linear independence and even basis, which we'll get to in a few more weeks. Why anyone cares? We'll attack that next Tuesday, okay? But today's going to be more of the abstract and general geometric interpretation and representations of span of a vector set and what linear independence means. In the last class, students asked a lot of questions, and I encourage you to ask a lot of questions to make sense of these ideas. I made the video before this class. So I took the set of 2.3 slides. I made the video that you're supposed to watch before you came, and I've made the other video, the video of the rest of the slides that you should watch before Tuesday. I should have made this one a little bit longer, and the other one a little bit shorter. That would have prepped us better for this class, but I apologize. Okay. So span answers the question of what are all of the places I can reach with a combination of the vectors that I have? What are all of the places I can reach? So combinations assume that you can take as many or as much of any vector as you want. So you can take one of them or 1/10 of them or 1,000th of 1,000 of them. And so the spans are always infinite because you can take things that are arbitrarily large. Unless you're dealing with 0 vectors and then you just have a point. But as soon as you have a vector that isn't a 0 vector, then the span could be a line that goes on for forever, or a plane that goes on forever, or a 3-dimensional space, or a hyperplane, like a 3-dimensional space in 4 or higher dimensions. But we usually just stick to 3 dimensions in this class because it's hard to visualize 4 dimensions. How come you're wearing an Ohio State shirt?
It's my wife's stepfather's, yeah.
Oh, well, let's burn it after class. Should we do that?
You can get me another CYU soda.
Another BOU school. How about the University of Michigan?
Yeah.
So I went to the University of Michigan. So Michigan wannabes. So all right. My in-laws live just outside of Columbus, Ohio. So my in-laws are Ohio State fans. So yeah. Okay, so span answers that question. If I've got a set of vectors, what are all the places I can reach with that? That's kind of a geometric approach. And there are similar questions like, is a given vector in the span? Like, can I rewrite one vector as a combination of others? Like this question here. So, can I write this as a linear combination of these? Or is the a linear combination of these vectors? You can ask this same question in a different way. You can say, is the in the span of S and T, because the span of S and T are all of the possible combinations of S and T. So in this case, the span, you write it this way. Well, the span of this set of vectors, the span of S and T, that is all combinations. So we could write it this way, where C1 and C2 are any real numbers. Okay. What does this look like? This should look familiar. What does this look like the equation of? A plane? This could be a plane. Okay. Does it have to be a plane? I put a question mark there, so you're a good student, so you already know that it doesn't have to be. If S and T already lie on the same line, if it's something like this or something like this, then this combination is only going to get you things on that line. So it could be a line. Okay? And there's one special case where it could be a point. If both S and T were the zero vector. If they were just the zero vector, the origin, no matter what combinations you got, you are still going to be at the origin. So it could be a point. It could be any of those. Okay? I'm just going to pull up a little website application for us. Okay. All right, here's, hope everyone can see this. Here we have two vectors, these black vectors, W1 and W2. I can change A and B, and that tells me how much of A and 1 of W1 and W2 I get. So for example, if I make this 0, then if I change B, then that just changes the length and direction of W2. And if I make that 0, then that would just change. I would just have different lengths of W1. But if I can change these, I can change both of these in ways, and I can move it kind of around. Now the question here is, can I get it to that purple? I almost had it to that purple a second ago, but oh wow, lucky. Okay, so I made it to the purple. If I moved this anywhere in the plane, can I get to it from W1 and W2? So I can, because they are linearly independent. Okay, they're pointing in different directions. So I have two different directions in R2. I can get to anywhere. So I don't know what I'd have to get. Oh, well, I was really lucky right there. Okay. one way to convince yourself that this might be possible, oops, or why this is possible, is as I move these values, as I just move one and another, notice I get, I can start getting a grid here. And the grid lines are parallel to the vectors. Oops. Right, you can see that the W2 is parallel to all the ones that are almost, what is that, vertical. W1 is parallel to the ones that are closer to horizontal. And so if you give me any point in the plane, I can just follow the grid lines and say, well, I need to go over this many W1s and up or down this many W2s, and I can get to that point. So I can actually find the combination using the grids in the same way that we use like the X coordinate and the Y coordinate of just one vector to the right, one vector to the left. We just count how many vectors over and how many vectors up. You can just do that with a different grid. Yes? In real life, yes, there'll be constraints. If we're just talking about abstract linear combinations, nope. So we just assume that C1 and C2, you know, that we can take, there are any real numbers, so you can take as many, they can be positive, they can be negative, so you can stretch them in whichever way. Right. Right. They probably wouldn't call it the span. I don't know what they call it, but yeah, you'd have a restricted domain on what it could be. Good question. Yeah, we'll talk about some real life stuff on Tuesday. I wish I could have got it in today, but all right. So here we're in 3 space. So I still have 2 vectors, W1 and W2, and I'm trying to match that purple vector V. The blue vector is still a combination of this. So I'm going to try to match up here. Oh, pretty close, right? Yeah, pretty close, aren't I? So it doesn't look like I can get it exact, but I can only jump in tenths. But if I jumped in smaller increments, maybe I could get it exact.
So when they're, are you saying that when they're linearly independent, it can be anywhere in like?
If I have 2, since our 2 is 2-dimensional,
Yeah.
and I have 2 that are linearly independent, then yes. In our 3, if I had 3 that are linearly independent, then I could get there. Even if I had 5, but I would still need 3 of those that would be linearly independent to expand R3. We'll talk more about linearly independence in a second.
That's linearly independent only intersects at one point, right? In R2?
Like any 2 vectors. Well, even 3 vectors would only intersect at a point. So I don't think that's quite the right way to think about it. I haven't thought about it much that way, so I could be wrong. But okay, so I'm pretty close here, right? No. Okay. I'm moving this around, and it doesn't look like I can get over there. Is it only because I can go up to 4? What's wrong here? I'm going to put on trace, and I'm going to move some things around here. Oops, I want to go this way. So this is kind of hitting a bunch of points that I can get to with those black vectors. Look at that. Those 2 black vectors lie in a plane. They are independent of each other. Right? They're not just, they don't lie just on the same line. That would mean they were dependent. But they are independent of each other. So I can go to any place in the plane that they lie in. So the span of those 2 vectors is the plane that all of those dots lie in. But V is not in that. V is not in that plane. So I cannot get to V. Okay? So V is not in the span of W1 and W2. if I were to try, let's do this problem, okay? So, so this is kind of a similar situation here. Is V in the span of W1 and W2? Here we have, is this in the span of this, or is this a linear combination of these? One way to solve, to see if this is true is to write this down as an augmented matrix. Okay? And if there is a solution here, because the solution would be an x and a y, where I'd have x times 2, 2, 1 plus y times 3 and minus 1, 2 would equal 5 and minus 7, 8. Okay? So I'm representing that here. I would have x's along here, y's along there, etc. And I could start row reducing. Okay? Some of you have already row reduced this, right? Did some of you get this? Oops. Okay, what did we get when you row reduced this? I'll assume that's a 1. I don't know. 1, 0, 0. 2, 1, 0. (23 minus 55). Okay, did other people get that? Something close? Okay. What does this say about how can we use this to answer this question or to complete this task? Some said no. Why? How do we know there's no solution? Yeah, because 0 equals non-zero, impossible. Once we get to this, we're like, oh, there's no solution. This vector does not lie in the span of these vectors. I cannot get to this point. If I think of this as a point, I can't get there by taking combinations of these. Okay? So are these linearly independent? I haven't given you a definition yet, so let's talk about that. I've talked about an idea of it, but a set of vectors is linearly independent. I think I already shared the idea. The kind of intuitive idea is if you can make one of the vectors by taking combinations of the other vectors, linear combinations of the other vectors, then they're dependent. But the definition the book gives and the place that they start, it looks a little odd at first. So it's linearly dependent if this equation, oops, KP. So the set of vectors, that's V1, V2, V3, up to VP, however many vectors that we have. If I want to see if there's combinations of these vectors that equal 0, this is the 0 vector. All those are vectors. C's are constants. Okay. This always has at least one solution. Right? You can always pick C's to be 0. If I take 0 of all the vectors and add them up, I'm just going to end up with the 0 vector. So if all the C's are 0, or must be 0, for this to be true, then they are linearly independent. Okay. So if you can make this true, it can be true. Where at least one of the C's is not 0, then it's linearly dependent. Okay. So I set up this equation. I want to know what combinations of the vectors I can use to get 0. I know I can always have one solution. That solution is if all my C's are 0. Okay. If that's the only solution, that's called the trivial solution. If it's only the trivial solution, then they're linearly independent. But if I can make this true by picking at least one of these C's to be not 0, then they're dependent. Yes?
Why does setting this equal to 0 tell us that, like, why does that work?
Why does that help? Because let me just write down a simple example. Suppose I have 3 vectors, vector 1, vector 2, vector 3. And I can say, okay, vector 1, 2 vector 1s plus 1 vector 2 minus 3 vector 3s equals 0. Then I'm going to show that my intuitive idea of linearly independent or dependent, if my intuitive idea was that, hey, I can make one of these by combinations of the other two. If one of these is not 0, one of these C's is not 0, then I can write one as a combination of the other two. So I can just solve. I'm going to solve for V1. So I can take V2 over a minus V2. I can take V3 over, so plus 3V3. So that equals 2 V1s. But now if I divide by 2, now I have V1. V1 is a combination of V2 and V3. I need half of V2, a negative half of V2, and I need 3 halves of V3. So now I have a combination. See, I can make V1 with V2 and V3. And I can always do that if I have at least one C1 that isn't 0, because if all the C1s are 0, I can't do that division. But as long as I can just take one of them where I have a coefficient that isn't 0, move everything else to the other side and divide. And so now I've written 1 as a combination of the other ones. So that means I can get rid of V1, and I can just use V2 and V3. And all of the combinations I could get with all of these, I could get with just V2 and V3. Yes?
So if the 0 vector is part of your set, does that mean they're always going to be dependent?
That is exactly right. So if you have 0, this is one of the slides I'll walk through in the next video. If you have a 0 vector as one of your things, I have 0 vector, vector 1, vector 2, however many vectors I need. If this is one of my vectors, well, I could always write down this equation and have 1 times the 0 vector plus, and I could always make those other ones, the coefficients to the other v's at 0. But I don't have to make this one 0, even though they still all equal 0. So yes, if you've got 0 in there, then it's always a linearly dependent set. Dependent meaning the idea of depending is, well, I can have V1 depend on this, and I can make it over here with V2 and V3. It's not independent of V2 and V3. So
whenever you're talking about independence or dependence, you need at least 3 vectors, right?
No.
Okay.
So
Like if I had only 2, like could I say that 2 are independent or dependent?
yep. So geometrically, if I've got 2, so if they're like this, those are, I've got 2 vectors, those are dependent. That's a dependent set. Or it might be, something like this. These are dependent. But these are independent.
Isn't that the same as if you have the zero vector in there?
Nope. They do always start at a, they do always have an origin. You know, these are, we're thinking of them starting at the origin. So the 0 point is in there, but not the 0 vector.
Okay.
So the 0 vector would be including that point, you know, the vector that doesn't go anywhere plus those or something. But there is something special about 2. There is something special if you only have 2 vectors. There's only one way to make one of these a combination of the other one. Make it a scalar. So like if V1 can equal C times V2. This is the only possible combinations you can have. So if you can, this makes it usually easy if you only have 2, you can just start looking, is this a scalar of this? Or I'd ask it this way in this case, what can I put right here so that these are linearly dependent? 6. And in fact, if I put anything other than 6, then they're linearly independent, because if I put this, if I make this 5, well, there's only one thing. I just have to look at one of these corresponding entries, one pair, before I know what the scalar has to be, right? 1 times what is 2? 2. This has to be, if this is going to be linearly, if this is going to be a linear combination of this one, this has to all be, these all have to be double this. So 1 times 2, 2 times 4, 3 times, oops. Yeah, so 1 times 2 is 2, 2 times 2 is 4, 3 times 2, I'd need a 6 there. But since it's not, then I know they're linearly independent. They're pointing in different directions. They're not on the same line. Okay.
Is that because the only way to make that true would be if all C's were 0?
Yeah, so if I called this V1 and this V2, then right now V1 plus so C1 V1 plus C2 V2 equals 0. What values could I pick for C1 and C2 to be 0, for this combination to be 0? Can you give me one? Yep. What are the possible values for C1 and C2? Yeah, 0 is one of them. Can I pick another one? Not with how they are right now. But if this is, but if that's 6, then I'm like, yeah, I could make this a minus 2 V1 plus 1 V2. And now it's 0. So, and that's, you know, this 2 here is the same, this minus 2 is related to the 2 that we would get when we multiplied that out. So, yes?
So over here, in the blue circle, that was linearly dependent, is that right?
Yes, this is linearly dependent.
So would you be able to do that with just 2 variables and show us like what that means graphically? Like, say you have some random equation that's like V1 equals
Yeah, let me see. I think I can do that with my this thing here. Actually, we're going to be in this situation. Okay. So here I have three vectors, right? And here I have a combination of those, A, B, and C. I'm trying to get to V, so I could ask the question, can I get to V or can I get to everywhere? I could start moving these around. I can get close there. But I actually didn't get it. And it turns out those 3 black vectors are not linearly independent. the span of those three vectors is just a plane. They're all lying in the plane. So I can get to any point. Let me just try to work in R2. Okay, here's two vectors, v1, v2. If I have a third, don't want to draw it so it looks exactly like the opposite of one of those other ones. v3, I can get to this point just by using these other vectors. So I can scale this one back here. So I can come back this way, and I can scale this one back like that. Then I can add those two vectors, and I'd get to that point, something like that. And this combination in this case of like a -1/2 plus 3/2, that just tells me how I scale each of these to get to this other one. So, yeah. So that combination says how you actually, it's like your recipe to get to here with these other vectors. Oh, I need some of this and some of this, and then I can get there. But that actually combination, here, let me rewrite this. I don't feel like I'm doing a good job of answering your question. So geometrically, what this means is I can get to the point represented by this vector in standard position by scaling v2 and scaling v3 and then adding those together. Right, adding the two vectors gets me, I put one on the end of the other one, right? So this tells me how far I need to go for one, how far I go for the other one, and I'll end up at that same position. So that's what that combination means.
So does that make the V2 vector there, the V3, those are independent, but then the V1 is dependent?
Yeah, we're not sure yet. The V2 or V3 may or may not be independent. This isn't enough information for us to know. But I do know that as a set, linear independence talks about a set of vectors. So these v1, v2, and v3 as a set are linearly independent. Okay? You can talk about like v1 is independent of v2 and v3. You can talk about it that way too. But this just says as a set, hey, then they're I know v1 is dependent on v2 and v3. I can make that combination. And I don't know yet whether v2 or v3, whether they're independent of each other or not. This isn't enough to know. So, okay. All right. Other questions? These are great.
So just to clarify, you're saying that, for example, if you three vectors in the same plane, that considering the set of all three of them together, they're linearly independent.
No, these are linearly dependent. These are linearly dependent because with these two, I can create this third one. So once I have, with just these two, these are independent. I can go anywhere in the plane. So if I add any other vector, it's going to be a linearly dependent set. So it's going to be extra information. I don't need that. I can already get to any point in the plane with these two. So once I add that, that's extra for me.
So if there's any vector that is dependent on the other, on like the set of vectors, then the set is considered dependent.
Yes. Very good. Very well said. Okay. Other questions?
So in R2, does that mean the max amount of independent vectors you can have is 2?
That's exactly right. Once you have 3 vectors, then you know for sure that it's 3 vectors in R2, right? So So if I take 3 vectors, I didn't even put out numbers. How comfortable are you guys without numbers? 1, 2, 3, 4, minus 5, 6. Okay. How would I know for sure that these vectors or any of these have to be a linearly independent set? I'm sorry, a linearly dependent set. Said that wrong.
So you're asking like, how do you know if it's, so either linearly dependent,
Yes.
if the first matrix is a, it can be a true scalar of,
That's a different question. So I threw up this to begin with, and I thought, oh, maybe I should just focus on numbers. So I have 3 vectors here. I'm saying no matter what 3 vectors you give me, that's why I put this up, A, B, C, D, E, F. No matter what 3 vectors you give me, they're going to be linearly independent. Sorry, linearly dependent. No wonder you guys are confused. I can't say it right. Okay. What's going to happen if I row reduce this? What's the highest rank I can have? 2, which means that's the highest number of pivot columns I can have. 2. I don't know what this would be. Question mark, question mark. Okay, it could be like this. I might end up with something like this. Okay, I could have pivot columns up to 2. And that means I've got a free variable, and a free variable means, oh, I can get that variable with these combination of these other 2. So, okay. You may not have known that right now, so I'm telling you, okay? When you row reduce, if you put your vectors into a matrix, and you row reduce, the rank of that matrix is the same as the dimension of the span. Okay? So the rank of that matrix is the dimension of the span. So once I get, you don't even have to go to reduced row echelon form. You just need to get to row echelon form. You just have to get to a point where you know how many pivot columns you have. Because the pivot columns is the same as the rank, which is the same as the dimension of the span. And any free variables, the number of free variables, is the number of dependent vectors in the set. So, so we're going to go back to using our row echelon form to just start seeing, like, are these independent? Are they independent? How many at most, how many independent vectors do I have in that set? Okay, yes?
so the last column can be a free variable?
Yeah, like, I mean, you could have this. Yeah, so this isn't an augmented matrix. Okay, so I don't have an augmented matrix here. I just put my vectors into a coefficient matrix and started row reducing. Yeah, so these.
So in an augmented matrix, the last one can't be a
That's right. That's right. Okay.
Also, I was going to ask you to focus on the homework problems. Because it wanted us to, like, determine just by looking at things without doing any calculations. Where it was like,
Okay, like this. Yeah, I think it's similar. It should be similar to this one.
I guess it was class one assigned technically.
Oh. Did it ask about, like whether it has a unique solution or infinite solutions? Okay. Why don't you send me an email, and then I'll make a video going through that, or I'll have one of the TAs make it. Okay. So I'm just worried it's going to take me a while to find it, but here. But let's look at this. Okay. Which of the following sets of vectors spans all of Rn for the appropriate n? So if I have so these are two-dimensional vectors. I have two coordinates, so I'm only in R2 here. These are two-dimensional vectors, so I am only in R2. I have three coordinates here, so I'm in R3. Okay, so look at those. See how many of you can come up with. It's got the clover, which means you can do. There's more than one of these you can mark. You're supposed to mark all that apply. So think about those for a second with what we've talked about today, and see if you can come up with some that you know for sure, especially if you don't have to do the work. That's really nice. If you don't have to row reduce all of these. You might have to row reduce some, but some of these we can just look at and say, I know that spans Rn, or I know that doesn't span Rn. Don't worry about this. Right, okay. I was just going to use it. No matter what you do, you could come up with at least the highest rank you're going to have is 2. So you're going to have one free variable. So that's what I was like. You're just stuck here. So, and then I put numbers so you didn't have to use the alphabet. So. Okay. Can someone just tell me one that they know spans the appropriate n? So for the three-dimensional vectors, for these are three dimensionals that have to do R3. These others are R2. So yes. The first one spans what? All of R2. How do you know? Okay, you only need 2 to span R2. You only need 2 independent vectors. Okay, and yeah, there's a nice slick way to know that this is independent of this one. It's not a multiple. Yeah, that's right. If you're only looking at 2 vectors, for them to be independent, one has to be a multiple of the other one. And one, you'd have to multiply by 3 to get 3, but 2 times 3 is not 4, so you know automatically, hey, those are independent. Geometrically, you're thinking about, well, those are going to be different. They're not going to lie on the same line, so you're like, that's going to convince you, right? So that's also good. Yes? That's right. If this was 3, 6, it wouldn't matter because they still have 2 vectors that are independent, and so they will span a 2-dimensional space. I'm only in R2, so that spans the whole thing. So sometimes we can do it that way. So yeah, like here, we already know this now. This spans R2 because that's the subset of right there. So how about this one? Will this span R3? Yeah. Does it span all of Rn for the appropriate n? Here we only have 2-dimensional vectors. right? We only have an XY, we don't have an XY and a Z. So will this span, yeah, will that span XY and, yeah, will that span R2? So we already saw, hey, these two are enough to span R2, even without that one. And so we already know that those are good. How about this one? Why not? We have the zero vector. So what can we say about this set of vectors? They're linearly dependent, okay? So what would the span of this, what's the dimension of this span? At most. 2 at most. In fact, we can check that it is 2 because this is not a linear combination of, like this isn't a scale multiple of this. So this, you can get at most 2 dimensions. If you were to row reduce this, you'd get two pivot columns or 2 rows with leading ones. And so we're only spanning 2 dimensions. We can't do all 3. Yes?
Now, if you had a third vector that was also independent, but still had a zero vector, would it be the that span? Like, would the span be there?
Yes. So if I added another one, as long as they were independent, I might have to start doing row reduction to verify that they are independent. So yes. Yes.
So what if we added a zero vector to the first set of vectors that we have for the 1, 2, 3, 4, 5?
It would still span. Oh, I should let you guys think about that. It would, because I still have two vectors. I can get to any points just with combinations of these 2. So it doesn't matter if I start throwing in others. In fact, any other vector I throw in is going to be it's going to be a combination of these 2, whether it's the zero vector or not. So yeah. Okay, how about this one? Nope. Yeah, we talked enough that this is a scalar multiple of this. So these would lie in the same line that only spans 1 dimension, won't span R2. What about this? Nope, we're still just on 1 line. What about this one? Okay, there is a clever way to think about this where you don't actually have to do row reduction. Did you guys do row reduction? How do you know that? Sometimes it looks that way, but okay. I think there's some good reasoning going on in your head. So there's we can't still use the idea of pivot columns here. This isn't in reduced row, it isn't in row echelon form. It's in kind of a row echelon form, though. And turns out if you get zeros up here in this corner, like you could be able to reverse it and get the zeros down there, and you have three pivot columns. But yeah, I think what Ian was saying is I can't use this one to make combinations of these because I'd have to multiply this one by 0 to make sure that those were 0. And so, but if I multiply those by 0, I'm not going to help make these. And a similar argument here, I have to, like to make this one, I can't use this one to make this one because I just have 0 here. So. Yeah, you can decide you can put them in however you want. If you're just going to row reduce and try to figure out. So, well, if you move them around this way, or you're talking about the columns. So yeah, so once you put them in one way, you can start switching rows and get it into row echelon form. Right, yeah. Because if you put it in 1, 1, 1, 0, 4, -2, 0, 0, 7, then you can start doing your your what are they called? Your elementary row operations, and move that one up. And no, we're still missing something, right? Yeah. So Yeah, so because you're creating the matrix, you're free to create the matrix however you want because they're just giving a set of vectors. So we'd like to make it in a different way, right? Right. So if we did 0, 0, 7, 0, 4, 2, and 1, 1, 1, yeah, then you can put that one up there and this one down there, and it is in row echelon form, and you can see you've got 3 pivot points. So that is nifty. So, okay, yes.
I don't know like the consistency of whether my rows or my dimensions or like columns. Like sometimes in the homework, like it'll be like x1, x2, x3 across the top, and then you'll have to like go put it into like a vector form that has x, y, z going down. So like in this example, for instance, from left to right, am I looking at x, y, z, or is that top to bottom? Does that make sense?
So the answer is yes. Like you can set it up, you can choose to set it up in different ways, and it partially depends on what you're setting it up to do. So if we're saying, are these independent, then I might say, oh, is there a combination that equals 0, 0, 0? And so I could augment these and have a matrix that was 1, 3, 5, 2, 4, 6, augment 0, 0. And then they would be X, Y, Z's. So I could think about it that way for that purpose. But depending on another purpose, you might think about it differently.
When we're talking about spans of vectors, like right now we're looking at vectors. We're not looking at a solution necessarily to the vectors, so we can move them around.
That's right.
It's not like there's a specific order.
Yeah. So if you're just checking to see, are these linearly independent, or so basically how many pivot columns I have, it doesn't matter where I put, how I make my matrix, that the rank of the matrix will be the same. But if it's a specific coefficient matrix and I start changing rows, if I start changing columns, then I'm interchanging values for x's and y's. And if you had x equals 2 and y equals 3, when you swap some rows, you might end up with x equals 3 and y equals 2, which has a different meaning. So, okay, we're done with time. Come with more questions on Tuesday. You can also email me. You can also join the Piazza group. I know 30 or so of you have, and get questions answered that way. And please send me the email on that homework question.